Hi guys, today we will continue our new topic. This is my second time recording this because again I forget to share my screen. Today I hope, let me check it again. Okay, I'm sharing my screen. Okay, and I am recording. Yes, everything is nice. Then we can start. Okay, so today we will continue construction of confidence intervals using pivotal quantity method. Actually, I will just summarize what we did last week related to this topic, and we will solve some questions. And then we will see how to find a pivotal quantity using distribution function methods. And then we will talk about the approximate confidence intervals and how can we derive confidence intervals for parameters of discrete distributions. Then next week we can start different constructing methods like general methods where we cannot have closed form CDF, or if you cannot find pivotal quantity using DF method or location scale family type, then how can we construct confidence interval? So we will see that, and it will be the end of the confidence interval. We will start hypothesis testing. Okay, so let me summarize what we did before. Okay, so let's start with pivotal quantities. Let's say we denote pivotal quantity by Q. So what makes pivotal quantity a pivotal quantity? It should be a function of some random variables. Usually we prefer to use a good statistics like maximum likelihood estimators or sufficient statistics to represent whole sample to estimate theta basically. And it should be a function of both sample random variables and unknown parameter theta. So these are the two must things. And when we look at its distribution, it should be free from any unknown parameter. Okay, so if you have more than one parameters, also it should be independent from all these parameters. So then under this case, RQ is a pivotal quantity. Okay, so it will play a pivotal role to derive the confidence interval. So how can we do that? And we need to find the distribution of Q. So what is the distribution of Q? So we need to find that. And after finding that, basically, we can find some upper and lower bounds with some probability. Then let's say we define the Cdf of Q as GQ, let's say. Okay, then what we will do after defining the CDF or PDF of Q, then we will consider some probability where our Q is between some upper bound and lower bound with some certain probability. It can be defined by delta or 1 minus alpha to give a relationship between hypothesis testing. So this will be our confidence level. Okay, confidence, how confident we are. Okay, so basically the probability that Q is between these upper and lower bounds. And this Q is a function of both x and theta. Then we can easily write this function in terms of theta basically. Okay, so our aim is to write this interval in terms of theta, and then since we are using probabilities, then upper and lower bound or the x values, some random variables will be a random variable. This interval will be a random interval. Then we need to convert this to a confidence interval by replacing random variables with the observed quantities. Okay, then how can we write this quantity? So using the CDF notation, it's easy actually to define those. So when we consider the distribution of CDF of Q, when we write upper bound in the CDF and difference between upper bound and lower bound basically gives us this probability. So let's draw the picture, okay? So let's say this is the distribution of Q, and let's say this is the PDF of Q. Q. And let's say its shape is something like that, okay? I don't know. Okay, so what we want to do, we need to find some upper bound and lower bound where our Q is between these with this probability, okay? And this point is QU, this point is QL, okay? And let's say with probability I for 1, we have this lower tail probability, and when we consider some upper tail probability, we have this, okay? So let's say this is a distribution. Okay, then, and we assume that here alpha equals alpha 1 plus alpha 2. So we can define equal tail probabilities. We can write alpha 1 and alpha 2 equals to alpha over 2. Basically, we saw that from the previous class. This minimizes the expected length actually when we choose alpha 1 and alpha 2 equal to each other. But let's make it very general, so we can use equal tail probabilities, no matter. Okay, so then basically, after seeing that, okay, so when we consider the CDF here, this one. So basically, we want to accumulate all the PDF till this point, okay, with this definition of that one. So what is the probability here? Then it will be 1 minus alpha 2, right? So this probability will be 1 minus alpha 2. Okay, so using this information, we can find QU, okay? Similarly, up till this lower bound, we know that the probability is alpha 1, okay? So the probability of this part will be alpha 1. So using this, we can define the value of QL. After finding the QU and QL quantities using the alpha 1 and alpha 2 values, okay, then so these parts will be known, okay? So we will find this one and this one, and then Q is a function of both sample random variables and theta. Then we can write this interval for theta alone, okay? Then after that, after defining it, then we will have a probability where we have theta L, theta, and theta U. Okay, this will be delta or 1 minus alpha. So theta L and theta U, these will be function of sample random variables. Okay, and also they should be a function of alpha 1 and alpha 2, and sample size and whatever. Okay, so the main thing here is this theta L and theta U are functions of random variables. So these are random variables. So the interval that we have here, theta L and theta U, will be a random interval, okay, not a confidence interval. Okay, random interval. So if we want to find a confidence interval, then we need to write one more step. Okay, so if you want to find 101 minus alpha % confidence interval for theta, then we need to replace, let me write it as function L, lower, where we replace all random variables with the observed quantities, okay? Then theta, let's say function. Actually, these are the numeric values of theta L and theta U at the end. Okay, so I will replace them, write it this way to show that we are using numerical quantities. Basically, F and L and F and U will be just numbers, okay? Where F and L should be less than F and U. So you have to be careful because we will not find numerical values. Actually, we will keep them as formulas. Okay, but you have to make sure that your calculations are correct and your lower bound is not greater than the lower bound, so upper bound. So you have to be careful about that. Okay, so this is how we are using pivotal quantities to be able to derive the confidence intervals. Okay, so we also covered how to find pivotal quantities actually. So this is one important thing. After defining our pivotal quantities, then we can find distribution and then we can construct all these. But the main thing is finding the pivotal quantity, what will be the pivotal quantity. So there's one theorem that we covered last time. It's about using the location scale type families. This is the reason why I start this semester by location scale families and location scale parameters, basically. So when our unknown parameter theta is a location parameter, then our pivotal quantity Q will be an estimator minus theta. This estimator has to have a good properties like MLE or a sufficient statistic for theta. Okay, and if you have a scale parameter, okay, then our pivotal quantity will be theta hat over theta. Again, this theta hat has to have a good property. Then our estimator represents the whole parameter good, actually. Then when we have a location scale type family, so we will have two unknown parameters in this case. Location family of PDF's case, and let's say theta 1 represents the location parameter, and let's say theta 2 represents the scale parameter. And in that case, when we want to find the pivotal quantity for theta 1, we are using, let's say, Q1, which is the estimated MLE or sufficient statistic for theta 1 minus theta over theta 1, over the second parameter. But in the pivotal quantity, there should be only one unknown parameter, so we replace the denominator part with the estimator. And for the second parameter, we have the second pivotal quantity. So we are using the same quantity for the scale parameter case, actually. Okay, so this will be the pivotal quantity for theta 1, and this will be the pivotal quantity for theta 2. So basically, we can generate confidence intervals for theta 1 and theta 2 separately by using this approach. But we have other methods that we can construct these intervals Q1 for theta 1 and theta 2 simultaneously, sometimes using like conformal inequalities and things. So we will not cover those things in this course. Okay, so last time we saw that one question, and in the lecture time on Wednesday, I also extra saw one more question. If you couldn't attend the class, actually, you can watch lecture video there. Records, actually, not the video. Okay, so let's solve one more question. So in this question, basically, we will not use location scale parameters, but first of all, we need to show that the given quantity is a pivotal quantity or not. So basically, we can define our pivotal quantities using location scale type families or distribution function method, or actually, if you can find by trial and error, or if you have some information like that, then you can find a pivotal quantity by yourself, okay? So you know the rules to be a pivotal quantity. It should be a function of some random variables. It has to be a function of a parameter, but its distribution should be independent of any unknown parameters. So if any quantity satisfies these properties, basically it can be a pivotal quantity. Okay, so let's solve this question. So let's say we have a random variable, a random sample, from a random sample from uniform theta and 1, where our theta is between 0 and 1. Oops, that's 0. Okay, first part says that show that Z, which is the first order statistic minus 1 over theta minus 1, is a pivotal quantity for theta where x1 is the first order statistic. Okay, so the given quantity is this one, x1 minus 1 over theta minus 1. So basically, it is a function of sample random variables, right? It's a function of first order statistic, and it's the function of theta. So basically, these two properties of the quantities satisfy. Then the third most important one, but these should be also satisfied, then distribution of z. When we look at the distribution CDF or PDF of z, it should be independent from theta. Okay, then find PDF or CDF of z and show that they are independent of theta. So we need to find the distribution of z. But before that, we need to find the distribution of the first order statistic first, and then to be able to find the distribution of the first order statistic, we need to find the CDF of x. Okay, so basically you can work with the CDF or PDF, it's up to you. Sometimes working with CDF is easier than working with the PDF, then you don't have to integrate anything to calculate, but it's up to you. Here in this solution, I use the PDF method actually. Okay, so let's start with writing the PDF of x. 1 minus theta, theta, x and 1. You can put an equality or not, it doesn't matter. Okay, so find the CDF from theta to x. Make sure that your integral, the upper boundary is x, not 1. Otherwise, you will get 1 as the solution, which shows you that actually you will prove that this is the PDF. Okay, so if you are getting 1 as the CDF, your upper bound of the integral is not x, but the upper bound for the random variable. So be careful about that. Okay, and this is the Cdf formula. After that, you know the formula for the first order statistic, PDF formula for the first order statistic, but I believe you know how to derive the CDF or PDF of the first order statistic. You learn it from the Probable course, I believe. Okay, so we have x1 where x is replaced by x1. Sorry, there should be no. Okay, and then 1 minus the CDF of x, where x is replaced by x1, get the n minus 1 power. Okay, so we have n over 1 minus theta. Okay, so 1 minus x1 minus theta over 1 minus theta to the n minus 1. Okay, so I have n. Let's see. So we have 1 minus theta, x1 plus theta. So we will have this to the n minus 1 and 1 minus theta to the n, right? Yep. Okay, so this will be the range. Don't forget to write the range. Okay, then after this, so this is the PDF of x1. Then we need to actually show that distribution of z is independent from theta. Then we need to do some transformation. Since I work with the PDF, I need to use the Coherence method here, the easiest way. But if you are working with CDF method, you don't have to do that. So it's maybe easier to work with the CDF. Okay, so here z is x1 minus 1 over theta minus 1. From here, we can write x1 as z theta minus 1 plus 1. From here, we can calculate the absolute value of the Jacobian as the x1 to the z, where it is theta minus 1, but theta minus 1 is negative, so it will be 1 minus theta. It's negative because theta is less than 1. Okay, okay, so let's write h of z. Okay, so we have n and 1 minus So what is x1? x1 is this one. So we have z theta minus 1 minus 1. Okay, so this plus b becomes minus and minus 1. 1 minus theta to the n. Don't forget to multiply this by 1 Jacobian. Okay. Okay, so this and this cancels out. So we have minus theta minus 1, which is theta minus 1 minus theta to the n minus 1, and we have 1 minus theta here. So basically this 1 minus theta to the n term, which cancels out, and we have the to the n minus 1. Okay, so we have to check also the range. So the range, so here x1, but x1 equals to this 1. So writing this again, so we will have theta minus 1, z theta minus 1, 0. Actually, this quantity is, negative. So when we convert it, we will have, 1, z 0. Okay, so then let's write PDF again with everything. Z1. So this will be the PDF. As you can see, it is independent from any unknown parameter. Okay, so this means that our Z is a total quantity for theta. Okay, then we can generate a confidence interval right now. So let's look at part B. Okay, part B says that find a 90% confidence interval for theta with equal tail probabilities. Equal tail probabilities. Okay. Okay, so we need to find upper and lower bound for Z. Okay, where the probability should be 0.9. So let's say this is our Q1, this is our Q2. So we need to find these first. And we know the value of Z. What was that? It was x1 minus 1 over theta minus 1, right? So we can write this in terms of theta. Then if we find the Q1 and Q2 values. Okay, so if we can write this as the difference of two Cdf values actually, right? Q1 equals 0.90. Okay, so this will be the Cdf of Z at Q2. So if you find the Cdf, it will be easy. You immediately put the Q2 value in that formula. But in this case, we need to find this. And we'll show that it's Q2 to the n. And similarly, when we do that, 0 to Q1, z n minus 1, dz. So it will be Q1 to the n. Okay, so let's draw the pictures. Okay. So let's say this is our Z, and this is our distribution. And let's say the shape is this one, okay? So it's not the correct shape, but I want to just show you the positions of Q1 and Q2, okay? So let's say this is the point Q1, and this is the point Q2 that we want to find. Okay, so we know that this is 90%. Okay, then we need to use equal tail probabilities. This means that for the tails, we have 10% when we equally distribute them. So this will be 0.05 and this will be 0.05. Okay, so these will be the tails. Okay, then using the Ctf approach, basically, we can say that up till this point, the Q2, the total probability will be 0.95, right? And similarly, up till Q1, our cumulative probability will be 0.05. Okay, so this means that this quantity will be 0.95 and this quantity will be 0.05. Then easily we can derive the value of Q1 and Q2 using this. Okay, then we can say that Q2 to the n equals to 0.95. Okay, and Q1 to the n equals 0.05. Then Q2 equals to 0.95 to the n. Or if you are familiar with this notation, you can also use this one. Okay, it doesn't matter. Basically, they are the same. And similarly, okay, and or if you are familiar with this notation, you can use this one. So 1 over n. Okay, so we found our Q1 and Q2. Okay, so probability that Q1 is 5. Now our z equals to x1 minus 1, theta minus 1, and 0.95 to the n, 0.90. Okay, then try to write theta alone here. After a little math, I will just give you the solution. Okay, so we have 1 plus x1 minus 1, 0.05, and okay, and theta, and 1 plus x1 minus 1, 0.95, and okay, equals 0.90. Okay, this is correct. Let me check. Okay, we have okay, so we should do like that. Plus 1 goes there. x1 minus 1 here. Multiplied. Yeah, it should be okay. So if something wrong, please let me know. Okay, so this is a random interval because we have random variables here, x1 term. Okay, then we can write our confidence interval for theta as 1 plus x1 minus 1 over 0.05 to the n, theta 1 plus x1 minus 1 minus 1 to the 0.95 to the end, okay? And so this will be our confidence interval. So then we have a sample. We know the sample size, whatever the minimum value, just replace it, and then these upper and lower bound will be just the manifold quantities. Oh, okay. Okay. So in this session, you also solve some questions, but to remind everything and so many more questions, I want to solve this question too. Okay, also let's say this is general information not directly related with the pivotal quantity or the construction of the confidence interval. But let's say our aim is not to find a confidence interval for theta, but a function of theta, okay? To be able to find the confidence interval for a function of theta. Then if that function is a monotone increasing function, all we need to do just apply the transformation to the parameter and also the upper and lower bound. You don't have to do anything else. So I just want to mention that because sometimes under the transformation, let's say we show that let's say our random variable is log normal distributed. So basically we know that log of x distributed as normal. And in that case, basically finding a confidence interval with log theta possible. But let's say in that case, we might need to find a confidence interval for theta, not for log theta. Since it's a monotone increasing function, logarithm is a monotone increasing function, all we need to do, take the exponent of the upper and lower bound to be able to find an interval for theta. Okay, so let me write these. So in general, if theta L and theta U is 100 delta % confidence in, and let's say theta hat is this is important monotonic increasing part, monotonic increasing, okay, function of theta in the parameter space, then we can find the upper and lower bound of theta, tau theta, by just applying this transformation to the upper and lower bound for theta. Okay, so this will be 100 delta % confidence interval for tau theta. Okay. Reverse is also true. Let's say we find the confidence interval for a function of theta, but we want to find the confidence interval for theta, and it will be a monotonic increasing function of the function of theta. Okay, then we can easily apply the same thing. Okay, so the example is based on this. So we would like to construct a confidence interval for theta. Okay, let's say theta hat is the MLE of theta, and we know that L and theta hat distributed as normal. Okay, but we want to construct an interval for theta. But knowing that, basically we can get a let's say L theta and something else, then we can construct an interval for L theta. Okay, so L theta hat plus minus Z(I)/2, let's say, and the variance of L theta hat here, the estimates. Okay, so let's say we obtain it as A and B. Okay, and to be able to find an interval for theta, we need to just convert this to, take the exponent, apply the same transformation here, and after finding this, so maybe it's easier to find this normal distributed confidence intervals than we have a normal distributed random variables. It's easier, you know. So just if you know that such an information, just apply that. Okay, and then with a little transformation, we can find the confidence interval for theta or whatever function that we want. Okay. Okay, so let's use a different approach to be able to define a pivotal quantity. Okay. Now we will use distribution function method, and actually here we will use probability integral transformation. I believe you learned this in probability course under the transformation section. Basically, we are using probability integral transformations for simulation purposes mainly, but there are other places that we want to use basically when we want to find a proper transformation that we need to apply to be able to obtain a random variable who has the specific distribution. We are using that, using distribution function, Cdf basically. Okay, so here actually we are thinking about any Cdf as a random variable, and then we can show that if we consider Cdf as a random variable, it is distributed as uniform 0, 1. Okay, so this is known as a probability integral transformation. So when we have a continuous random variable x with a PDF f of x theta, then we can calculate its Cdf, right, by using the probability that x less than or equal to x. And we know that this quantity, since it's a probability, should be between 0 and 1. And you can prove that if we consider this f as a random variable, okay, that is distributed as uniform 0, 1. Okay, so any Cdf is a random variable distributed as uniform 0, 1. So this is known as probability integral transformation. Okay, so basically the main aim as simulation purposes, you know, any random number generator is actually distributed as uniform, because any number in specific range has the same chance to be selected actually. So this is the basic property of uniform distribution. If you are giving some range 0, 1, any specific value has the same chance to be selected. So when we want to generate data from specific distribution, let's say exponential, then what we are doing basically, we have the Cdf of, we can find the Cdf of exponential distribution. When we consider that Cdf as a random variable, which is 1 minus e to the minus x over theta, x is capital letter right now, so we have a random variable. So if you know that this is uniform distributed, and if you want to generate a data from exponential distribution, so what we need to do, just generate random data from random number generators where the range is between 0 and 1, and then equate these numbers that you generated to 1 minus e to the minus xi to the theta, and then solve for x. Okay, then we will get x1 equals something, x2 equals something, but you have to define some parameter value actually from specific exponential distribution with a given parameter. Then you will have a data from exponential distribution, not from the uniform. Okay, so this is the basic aim that we are using probability integral transformation. But to be able to derive the pivotal quantities also, we are using this approach. Okay, so you knowing that actually, so if you have a Cdf, then you see that it is distributed as 0 and 1. So Cdf is a function of x and also unknown parameter theta, and its distribution is free from parameters. So using this approach, basically we can create pivotal quantities. But this form is not that easily derived. So we know that when we apply some kind of transformation, like minus ln transformation to the uniform distributed random variable. So this is, let's say, ln f of x theta. This has an exponential distribution. Okay, so you can show that. You know, exponential distribution is actually some special form of gamma distribution with parameters 1 and 1. Okay, and from here, basically we can generate chi-square random variables who has some statistical table. So the calculations or construction of the confidence intervals will be very easy if you use this information. Then when we consider another transformation, W, let's say it is 2 times Z, okay, which is minus 2 times ln f of x theta. Okay, so then this will be gamma 1, 2, so which is chi-square with 2 degrees of freedom. Okay, so now we have parameters. We have a function of a random variable and a parameter whose distribution is free from theta, and we can easily use this distribution to be able to get table values. Then construction will be easier. Okay, so this is for just when we have one random variable. Then when we have a random sample, for a random sample, when we add them up, okay, so WI is basically, so minus 2 times summation of ln CDFs. Here we are using the Coherence Theorem, basically. The independent summation of independent chi-square distributed random variables will be chi-square, where we are sum the degrees of freedom, so it will distribute as chi-square with 2n degrees of freedom. Now we have a function of some random variables. Okay, so this will be a function of some random variables and theta, and its distribution is independent of theta. So this means that this quantity then is a pivotal quantity for theta. Then we can easily derive confidence intervals using this pivotal quantity. Then we can say that in probability, okay, so we have pivotal quantity, we have, which is this one, and we have upper bound and lower bound, and this will be, let's say, 1 minus alpha. So we have a chi-square distributed, chi-square with 2n distributed variable. Okay, so we have right skewed shape like that. So we have an upper bound and lower bound. Okay, and we want this probability will be 1 minus alpha. And we show that for a chi-square distribution, when we use equality probabilities, basically we obtain the expected minimum length. Let's say this will be alpha over 2. And this probability also alpha over 2. So this point, we are using upper tail probabilities, remember chi-square 2n with alpha over 2 degrees of, probability, and the upper tail probability here chi-square 2n 1 minus alpha over 2. So what we have to do, just replace an upper bound and lower bound from tables, chi-square tables. Okay, alpha over 2. And then solve this for theta. Then we obtain a random interval, then replace capital X's by the lowercase x's, then make sure that it is numbers, and we obtain the confidence intervals. Okay, so let's do some examples. Okay, so this is a simple example, exponential example, and actually, we will end up with the same interval that we obtained by the scale parameter approach, okay? But it's not necessarily correct for any cases. Basically, we can have two different confidence intervals using different techniques, like for location scale parameter approach. We can derive another different interval for pivotal quantity using DF distribution function. We can have a different one, or using general method that we will learn, we can have a different interval. So you need to choose the best one, and the best one will the one who has the smallest length, actually. Okay. Okay, so we need a CDF here for. Okay, so let me write the PDF first. So we use this form of the exponential PDF, you know, and then the CDF, we can easily calculate the CDF as this one. Then, when we consider this as a random variable, okay, so this has a uniform, let's 0, 1 parameters. Then, okay, when we apply -2 Ln transformation, it will be chi-square 2 degrees of freedom. And assuming that we have a random sample of size n, then we will have -2 times summation Ln f of xi theta. Yeah. This will be distributed as chi-square with 2n degrees of freedom. This will be always the same, okay? So chi-square 2n. So you don't have to find the distribution of the pivotal quantity like the previous case. So this is always chi-square distributed with 2n degrees of freedom. Okay. Okay, so here, actually here we have one, how to say, make our life easier case. Okay, so instead of this f of xi, because in many, for many distributions, our CDF is in 1 minus format when we are using the, let's say, the order statistics, we can have this type of thing, and exponential distribution, we have this. If our CDF is in 1 minus blah blah type format, okay, then instead of using f of xi, we can use 1 minus f of xi. If f of xi is distributed as uniformly 0, 1, 1 minus f of xi will be also distributed as uniformly 0, 1. Okay, so if our, let me start from here. If our Cdf is in 1 minus blah, blah, blah format, then use 1 minus f of xi theta instead of f of xi theta. Okay, so then in this case, the calculations will be easier and you will get the same result. Okay, so ln 1 minus f of xi theta. So this will be also chi-square with 2n degrees of freedom, and your calculations will be easy. Okay, so since our PDF is in this form here, so 1 minus blah blah format, then okay, so let's use that. Minus 2 times summation I from 1 to n ln. Okay, so 1 minus 1 plus e to the xi over theta. So this will be our pivotal quantity. Okay, so this one terms cancels out. So this will be distributed as chi-square with 2n degrees of freedom. Then we have minus 2 times summation ln e to the minus xi over theta. So what we have here is, we can write this as, okay, so let me write one more step, minus xi over theta. So we have 2 times summation xi over theta. Okay, so this will be our pivotal quantity. Okay, so this is a pivotal quantity whose distribution is chi-square with 2n degrees of freedom. So in the construction of the confidence interval, right, in the probability, so we have our pivotal quantity, which is this one, okay? But now we know the upper bound and lower bound. Okay, so our lower bound is 2n upper tail probability and chi-square 2n with upper tail probability. Okay, so only thing that we need to do is write this for theta, okay? Then actually we will obtain the same interval that we obtained by the scale parameter approach. So 2n upper bound goes here, theta, because it's reversely related, xi chi-square 2n 1 minus alpha 2, 1 minus alpha. Okay, this is a random interval. Okay, don't forget. And then write the confidence interval for theta as replacing random variables with the observed ones. Chi-square 2n alpha over 2, theta 2 summation xi. Okay, chi-square 2n 1 minus alpha over 2. Okay, so don't forget to replace these. Okay, to have a confidence interval. So confidence intervals should be a numeric quantity. Okay, so not a random variable. Okay, so we obtain the same interval that we obtained by the previous case. Okay, so let me show you one more example. Okay, so this is a Pareto example. So let's say this is a random sample from Pareto distribution, where X is distributed as Pareto with these parameters. Okay, so the Cdf is given to us right now as 1 minus 1 plus x to the theta, x greater than 0. So this is the Cdf. And as you can see, Cdf is in form 1 minus blah blah format, okay? So instead of working with this, we may prefer to use this to make the calculations easier. Okay, then using the Cdf method, we can find our pivotal quantity as minus 2 times summation ln 1 minus Cdf as minus 2 times summation ln 1 plus xi to the minus theta. And write one more step, so we will have this I from 1 to n as, so this is as chi-square distributed with 2 n degrees of freedom, and this will be our pivotal quantity for theta. Okay, then we can use this to derive the confidence interval for theta. Again, we will use the same approach. We know the distribution, so the lower bound will be chi-square 2n 1 minus alpha over 2, and our pivotal quantity and the upper bound with chi-square 2n alpha over 2, 1 minus alpha, let's say, and write this interval for theta. Okay, so probability that we have chi-square 2n 1 over 1 minus alpha over 2, and we have 2 times summation ln 1 plus xi. In the middle, we have this, and the upper bound over 2 times summation ln 1 plus xi. Okay, so this equals to 1 minus alpha. Then 100 1 minus alpha percent confidence interval for theta. Okay, here is, okay, so we will have chi-square 2n 1 minus alpha over 2, so 2 times summation ln 1 lowercase x theta, and chi-square 2n alpha over 2, 2 summation ln 1 plus xi. Okay, so this will be the confidence interval. So sometimes the question is not just finding the two-sided confidence intervals, but upper or lower bound for the confidence interval. So at that step, actually you have to focus on your pivotal quantity. Your pivotal quantity is an increasing function or decreasing function of theta or not. So in this case, for example, our pivotal quantity here, so that's 2 times. Oops. 2 times summation theta ln 1 plus xi is an increasing function of theta, right? Then if you want to find an upper bound for theta, then we can use the upper bound for the pivotal quantity, okay? Or if you want to find a lower bound for theta, then we can use the upper bound for the pivotal quantity. Okay, so basically, so 2 theta summation ln 1 plus xi, giving this 2n alpha over 2, basically gives us immediately an upper bound. So not alpha over 2, sorry, we are working with the one-sided interval. So we will get 2n alpha 2 summation ln xi. But if our pivotal quantity is a decreasing function of theta, like this case, okay, so our pivotal quantity is 2 times summation xi over theta, so it's a decreasing function of theta. So when we want to find an upper bound for theta, we need to start from the lower bound of the pivotal quantity, and we will end it up with the upper bound for theta. So you have to be careful. It's not a difficult thing, but you have to be careful when you are working with the one-sided intervals. Okay, so after this, okay, so we can start the approximate confidence interval concept. Basically, here we are mainly using central limit theorem. But also we can use the asymptotic distribution of MLEs. You know, if you remember from the last part of the first semester, we proved that, we showed that the asymptotic distribution of MLEs are normal with some parameters. So we need to define the Fisher information and stuff. But we can find an approximate interval using this approach also. Okay, so the second approach is the approximate confidence intervals. Okay, so first approach. Let me use this color. Okay, so let's say we have a random sample of size n. Usually we assume that. Remember what the central limit theorem tells us. So when we have a standardized sample sum or standardized sample mean, limiting distribution of these will be standard normal. Okay, so what central limit theorem tells us that one. What we mean by standardized sample mean, so we have a sample mean, but we are standardizing it by subtracting its mean and dividing by the standard error. Okay, so on the limit, it has a standard normal distribution. Okay, we can use some version of that one. Instead of x bar, we can write summation of xi and mean and the standard error of some xi can be considered also. Okay, so actually when we consider this, when we look at the quantity here, so we have an unknown parameter mu here, an unknown parameter sigma. So if sigma is known, everything is okay. But let's say sigma is unknown, but it's a function of mu. In that case, basically, we can define our this quantity as a pivotal quantity. Okay, so this will be a pivotal quantity if our sigma will be a function of mu. Okay, because it will be a function of some random variables, which is x bar here, and unknown parameter mu. Sigma is a function of mu, so it will be not another function. And then its distribution not depend on any parameter, okay? So basically, we can treat the standardized sample mean as a pivotal quantity if sigma is a function of standard error, standard deviation is a function of mu. Okay, so usually we are seeing this type of thing for the discrete distributions. Okay, so let's consider a binomial distribution. So let's say we have a binomial distributed random variable with sample of size n and success probability mu. So here, when we look at the sample mean, it's n times p, and when we look at the variance, it is n times p times q. So it is a function of p, mu, in this case, as you can see. Our q is 1 minus p, know that. Okay, so here, remember when we have two outcomes, of a fixed number of events, and let's say, and these experiments are independent from each other with the same success probability p. So we have an independent Bernoulli trials. Then some of the occurrences will be binomial distributed. So you know how to generate binomial, how we have the binomial distribution. So basically, we can treat our binomial random variable as a sum of Bernoulli trials. So basically, each trial are independent from each other. We have two outcomes with the same probability. So we can treat our y as a sum of independent Bernoulli trials. Okay, so this will be sample sum from Bernoulli P. Okay, and assuming that in the binomial case, basically each x1, x2 to xn independent from each other, and they are identical, basically independent and identically distributed. So we have a random variable, Bernoulli P. Okay, so this is how we generate basically the apply the central limit theorem. So when we consider the proportion here, we showed that from previous semester this y over n is the best estimator for p. Remember, proportion of occurrences in and trials. Okay, when we consider this expectation, okay, so n times p over n, so we have p, and when we consider its variance, so we have n times p times q over n squared, so we have pq over n. So basically by using the center limit theorem, we will have, let's say that equals to p hat minus p over pq over n. And the limit, we know that it is normally distributed. So we can treat this as our pivotal quantity. Then we can write in probability, the set is n minus Theta f over 2 and plus Theta f over 2 with some given confidence levels. Okay, and from here, writing the value of z here, we can find an interval for p. Okay, so we have z f over 2, p q over n, z similarly p hat plus now f over 2 pq over n. Okay, so this is 1 minus alpha. Okay. Okay, so but this interval contains unknown parameters, so we don't know this part. So this is the main problem here. So we need to get rid of this quantity. So this is an approximate confidence interval, if you remember. So we have 3 approaches, but I will just show you the 2 of them. The third one is for an approximate confidence interval, too many calculations. So I don't want to give this to you. So a very simple solution here is replacing p and q by the p hat and q hat values. Okay, so for large sample sizes, basically assuming that p hat converges to p in probability, then we can basically this is approximately true. Okay. So replace p by p hat here. Okay, then 100 delta % approximate confidence interval for large n for p will be. Okay, so we will have p hat, we replace the numerical value now, z f over 2. Now we have p hat, 1 minus p hat, we represent them by q. Okay, so we will have this one. So this will be one approximate confidence interval. Another approach here, okay, so one approach is here, let's say A, or we can find the maximum deviation that can be obtained by any sample. Okay, so this part is related with the error term that we have. The variation of sample will include the sample variation, basically. So we can consider the maximum error that we can do there, and we will have a very conservative confidence interval under the largest variance assumption. Then we need to consider, in that case, maximizing the P and Q part, okay, in terms of P. So this means that, so this is an optimization problem. Just take the derivative of this one, 2P equals 0, then we obtain P equals 1 over 2. And then we can consider the second derivative to make sure that this point as the maximum point, we obtain -2. So this gives us the maximum point, basically. Okay, so the maximum value that can be obtained for this will be 1 over 4. Okay, so this is the maximum error that can be done. Okay, so when we consider the shape here, so we will have this type of shape, we know that it's concave down. the value for P is 1/2 here, and here is 1/4. So we found this maximum point. Then under this condition, then 100 delta percent conservative and approximate confidence interval for theta. So basically this will be the confidence interval under the largest variance. Okay, so it will be like P hat plus minus delta F over 2, 1/2 square root of n. So this cover all, possible sample variations. Third approach actually considers a polynomial, second order polynomial solution. So I don't want to give that one, it's very long. Okay, so, and actually it's just an approximate interval, not an exact one. For an approximate interval, it's too many calculations actually. Okay, so another approach actually to find the confidence, approximate confidence intervals is using the asymptotic distribution of MLE. Use of the asymptotic distribution of MLEs. Okay, so if you remember, let's say we have X with PDF of theta, where we assume that theta is a single unknown parameter. So we don't have other unknown parameters. We can have, but in this course we are not focusing on these. Okay. And let's say theta hat is the MLE of theta obtained by differentiation, not intuition. Obtained by differentiation. Okay, then under this condition, we can find the asymptotic distribution of the MLE for large n, okay, as normal, with mean theta, and the variance equals to Cramer-Rowe lower bound for theta, which is 1/n times Fisher information that we have, okay, where the Fisher information I theta equals minus expectation of second derivative of ln f of x theta d theta square. Okay, and after that, basically standardizing theta hat by these quantities and I theta. This is approximately for large and standard normal. Then, so this will be our pivotal quantity, okay? And this distribution is free from any unknown parameters. Then using the approximate operand lower bound as minus the F over 2 and plus the F over 2, and solving for unknown parameter theta, so we can derive approximate confidence interval for theta. Okay, so let's look at one example. So this is an exponential example. Since explaining things with exponential is easier, so I usually use exponential in the when I want to explain the procedures with an easier PDF. Okay, but we will solve other questions also. And there is station related to these actually. Let me see, we don't have. Okay, so let's say we have exponentially distributed random variable. Actually, here, we don't need to derive an approximate confidence interval for exponential distribution. We already derived the exact distribution, remember, using the chi-square distributions, using distribution function method, and using the scale parameter approach. We already defined the exact intervals for theta. Okay, so I'm just showing this to you how to use this approximate approach by using Fisher information and Kramer rollover bound approach actually. Okay, so this is just an example. You need to prefer always the exact intervals. If it's possible to derive exact confidence intervals, prefer those because they are precise. The other ones are valid for large and approximate values. How large? So it's up to the random variable that you have actually. Okay, so always prefer the exact ones. If you have two different exact solutions, then choose the minimum one. But if you have one approximate, one exact, prefer the exact intervals. Okay. So here are MLE as X bar. You know how to calculate that. I don't want to give it to you right now. And then we can derive the Fisher information. Maybe you don't remember the Fisher, how to derive the Fisher information, but first of all, we need to find the ln of PDF. Okay, so we have minus ln theta minus x over theta. So this will be the log of PDF. Then take the derivative of this with respect to theta. So we will have minus 1 over theta plus x over theta squared. Remember, this is a score function. And if you want to check everything is okay, or if your calculation is okay or not, you can check this expectation is 0 or not. In this case, actually, we will have minus 1 over theta plus expected x is theta. Remember, for exponential, so it is 0. So everything is nice so far. So we will have 1 over theta squared minus x over 2 theta cubed. Okay, so finding the minus expectation of this will give us the Fisher information. We discussed everything actually previous semester. What is the meaning of taking the second derivative? What we are measuring actually with the Fisher information. We already discussed those, but here I'm just calculating the Fisher information because we need to find it to derive the approximate confidence interval right now. Okay, so I'll put this. Okay, so we have 1 theta squared plus 2 times expected x over theta cube. Expected x is theta, so we have 1 over theta squared here. So this is the Fisher information. So this means that, okay, okay, then we have MLE minus the parameter we have, and 1 over the square root and times the Fisher information we have, which is 1 over theta squared. Okay, let's try to write it in a nicer way. So we have square root of n x bar minus theta over theta. So this is approximately large and normal with 0, 1. Okay. So this is our total quantity. So it seems like we have both theta in the numerator and denominator, but after some little cancellations, so what we will have will be x bar over theta minus square root of n. Basically, we have just one theta term, okay? And this will be the normally distributed random variable approximately. Large n. Okay, so this will be our total quantity for theta. Okay, then in the probability, we have minus Zf over 2. Our total quantity, we have x bar minus theta square root of n Zf over 2. So this is 1 minus alpha. So this is an approximate confidence interval. Okay, okay. Let's see. I have this calculated ones. I hope it's correct. Let me immediately write it, but if it's not correct, please let me know. X bar plus Z over 2 X bar over square root of n theta, and we have 1 X bar minus Z over 2 X bar over square root of n alpha. Okay, so after that we can write 100 1 minus alpha percent approximate, okay, confidence interval for theta as, okay, so write the lowercase versions of X bars, Z alpha over 2 X bar over square root of n and theta, and we have 1 X bar minus Z alpha over 2 X bar over square root of n. Okay, so this will be the approximate interval generated by the asymptotic distribution of these. Okay. Okay. So we have one more approach actually that can be applied. This is actually the approximate method. But in this case, mainly in discrete cases, like for the binomial case or Poisson case. So what we have in these cases, actually, both, actually the variance part is a function of the main parameter that we have. And it's not that easy to get rid of that parameter value in the variance part. So another approach can be, think about one transformation, okay, which makes the variance of a random variable is free from unknown parameters. So then we will have a constant variance in that case. This method is known as delta method, okay, where we apply, actually, you know, Box-Cox transformation, that we apply Box-Cox transformation to make sure that our distribution is normally distributed or our variance is constant. Remember, for time series cases, sometimes we are using that to get stabilized variance. So basically we apply delta method. So today I will stop here. Okay, so next class we will see how to find an approximate confidence interval using delta method. So here we will use Taylor series expansion, approximated function by Taylor series expansion using the first two terms, and then apply the delta method, apply some kind of transformation to the variance, and then develop an approximate interval. And then we will see how to derive a confidence interval using general method. So in this case, we will not work with the pivotal quantities. So for, let's say, for a scale parameter, how can we derive the values? Or for, you know, if we cannot find the distribution function, if our distribution function is not in closed form, how can we derive the interval? So general method gives us the general approach to construct the confidence intervals. But the results may be different. Let's say we can construct a confidence interval using pivotal quantity methods by DF or scale location type, or general method. They can be different than each other, so we can end up with different intervals. Again, I want to repeat it. So you have to select the interval with the minimum length. Okay. Okay, then let's stop here. So I will see you in the class on Wednesday. Okay, so I will prepare also the H5P version of this one. Don't forget to watch that one, or at least try to solve the problems there when you reach that little dots. Okay, so see you guys. Take care. Bye-bye.